Hello, I'm Ecklin Crenshaw, and I'm going to talk about the use of robots for material discovery. This presentation is broken up into 5 sections. We have our introduction, where I will give a little bit of context of what laboratory automation is. We will follow that up with the current capabilities we have in our lab. Then we will take a look at the research we are currently performing, followed by a change in project structure, because with laboratory automation, we had to rethink how we do research and how we structure our projects and teams. And then finally, we will look at the future and where we are planning to go. Laboratory automation can be broken up into 2 sections. You have your software side and you have your hardware side. Your software side generally consists of data processing, data analytics, experimental design, iteration, concepts like that. Hardware, you're looking at the physical pieces of equipment that do the experiments. So you're looking at liquid handlers, you're looking at solid handlers, you're looking at sample movers. Why are we interested? So we are interested in laboratory automation because we increase our reproducibility, we increase our accuracy, we can increase our throughput, so we can do more samples, more experiments in a faster amount of time, but most importantly, we free up our scientists to work on more complex tasks. So, laboratory automation can be broken down into different levels, similar to how self-driving cars are broken down into different levels, where with cars, you have your level 0 being manual, so the driver is focusing on the task of driving, they're interacting with the world, they're doing that sort of thing, and where for cars also, you have your level 5, which is fully autonomous, so the car is now focusing on the task of driving and interacting with the world. Laboratory automation is very similar. We have our level 0 through level 5, but it's broken up into 2 sections. We have our hardware and we have our software side, where we start off with the human or researcher performing experiments. They're handling the samples, they're handling the tools, they're doing all that sort of thing. Then we start to automate specific task in the experimental setup. So now the robot is doing, so now we have robots doing parts of the experiment and humans doing other parts. Then we start to work into fully automated experiments. So now we have hardware systems that can do the actual experiment themselves. They can move samples, they can do that sort of thing. And then lastly, for the last section, you have your fully autonomous lab, which takes care of itself. It resupplies, it handles the equipment, it does all that sort of thing. For software, you start with your human-driven again. So the human is thinking of the experiment. They're focusing on the data. They're thinking about the next experiment and the one after that and stuff of that nature. So then you start to create software that does singular iteration designs. So it's suggesting future experiments based on previous data. Then you start to accelerate and move into multiple iterations of design. So the system is now thinking of multiple experiments based on previous data, and then it will take data from completed experiments and then continue a loop. And then you have generative automation, which will be the system thinks of the experiment based on literature and what's available in the market. And both the automated lab and the generative gives you a level 5. So, because you guys could not come to our lab, I have tried to bring a portion of our lab to you guys in the form of videos. So let's take a look at some of our capabilities. So this is our liquid handler. We also call it cell 1. Moving from left to right, we have our UV curing system. Over on the far left, we have our formulation or our deck. This is the main sort of area the experiments are generally performed. And then we have inline characterization for collecting data. The inline characterization is built of a spectrometer and haze meter. Below, we can see various actions that the system can actually do. So we have internal robotic arms for moving samples and substrates around. It can move samples and substrates on it, around the deck or off the deck. We have 8 independent pipetting channels, so we can aspirate different amounts of materials to different locations on the deck simultaneously. We can uncap vials, we can recap vials. We have heater shakers, which will heat samples and shake them. They go up to 125 C from ambient temperature. And then we also have a external robotic arm that will move samples from the main housing to the characterization stations. Cell 2 consists of our solid handling robot. We can see on the left some of the main actions that it can perform. It is relatively simple in concept. It is an automated balance with an integrated robotic arm. The robotic arm can move adapters, vials, and dosing heads into the balance itself. The dosing heads are what holds the solid materials. When the dosing heads are placed in position above a vial, the balance will actually lower the dosing head to a preset distance from the vial and start dispensing solid material. The neat things about these is that each dosing head has an RFID chip built into it, and they are stored on an RFID chip reader. So we can actually monitor the position of each chemical without telling the system where it is, and it will keep track of how much is in there and the general chemical properties of what's in the dosing head. So our last system is the PAL system. This is Cell 3. It's a processing robot, super customizable. It can uncap, it can recap, it can transport different samples and substrates across its deck, either through a magnetic mechanism or a physical mechanism. It can shake, it can actually switch out its tools that it has installed based on your workflow into the gantry. So depending on what you want to do for this particular set of experiments, it will go and retrieve your tool. So if we go back to our levels of automation currently, and we think about what automation we have in our lab right now, we are currently sitting at a level 1, level 2 automation lab. And every day we are moving further into level 2, automating more of our experimental workflow. So what are we using all this automation for? Let's take a look at some of the research. So we started off doing organic dye synthesis. We can see here we started with some starting material, and through a chemical reaction we have produced this product. This product was our first time ever actually using the robot, and we produced a new material ever that's we cannot find reference to in any of the literature, and it was produced in our robot. And we can actually see through this time measuring spectra that the change from your starting material to your new material here. Because the way we are using these machines, these systems, and not aligned exactly with how they were originally designed, we've had to rethink how we do research, especially for material science. And in this case, we've had to design our own hardware for the systems. So here we have some labware that we designed to support our research. We have our shell valve racks, which is our standard racks that we use. It can hold shell valves and our standard 4mm valves. We've also started to use quartz cuvettes for their optical properties. And here we have our Gen 1 and Gen 2, improving on the design in Gen 2. Next, we started to work into inorganic synthesis. Here we took a tridentate and a bidentate, and we made our product. In this particular experiment, we made 18 unique compounds all at the same time, which is very rare. Here, again, we started to use new labware. We actually designed this 2-part valve rack to reduce in weight, because we would notice that the internal arm would struggle moving our single valve rack. So we designed this one to reduce weight, and it works like a charm. So a big area of research that we are currently doing is our crystal growth and our hybrid organic inorganic materials. In this particular set of experiments, we grew these crystals in cell 1 using both cell 1 and cell 2. We started to utilize machine vision to start to recognize points of interest. So we can see here is a rendering of that machine vision, highlighting what we are interested in, and then we were able to generate a reflective spectra off that data. Similarly, we also do our hybrid organic inorganic materials, which are single crystals. For this one, we utilize heat is very important, and this distributing the uniformity of the heat is important. Here we used the machine shop on Wright-Patterson base to create our own heating blocks that were based on the original Valrac's design. And lastly, we have originally worked on these liquid crystal designs. Here we had to redesign our substrates from the ground up. We can see on the far left here is our handmade cells that we typically use for our research when a human is doing it. So that's 2 ITO-coated glass slides with a LC material sandwiched between them. You're able to apply electric potential to the glass slide and get a physical response to the LC material. The form factor does not work that well for the Cell 1 or the liquid handling robot. So we went back and I designed these first-gen cell arrays, which consist of 35 independent cells. They have the same dimensions as a standard well plate, and since these units are generally built for biological systems, they use standard well plates primarily. But unfortunately, these designs were not ITO coded. So we went back to the drawing board and we created a new assembly process for these Gen 2 cell arrays, which are ITO coded, so they can be electrically triggered. But we had to reduce the number of cells while increasing the gap length for this production process. So, if we compare the work output of the max work output for a human versus the max work output for our robotic systems over a period of week, we are looking at a 40 to 60 time increase in efficiency between the two, right? So the robot can do a lot more samples than any human can do that week. For many of these projects, we have also collaborated with the Army, Duke, VMI, and a couple other institutions. So because we had to go back and think about how we do research for these projects, we've also had to go back to think about how we structure our projects. And for this, we started to use project management tools such as Gantt charts for scheduling to increase efficiency, to increase communication between the group, especially since there's multiple scientists working on the same project at different phases. So we started to use the tools that were designed for industry. So now that we have looked at what we have been working on, let's take a look at what we plan to work on and what we hope to work on in the future. Here, we have many focuses that we want to go after in the near future and the far future. One of those is data processing, data analytics. We're lacking on the data software side, and we are planning to partner with Rick and his team to try to develop these tools. So we want to start using like cloud-based analytic tools for data processing, and we want to start implementing like a LIMS system for data management. We also plan to do some scale up, so more samples per run, per experiment, and also use larger vial sizes. And then lastly, we have in the near future plans for upgrades for cell 1, 2, and 3. So if we, on the far left there, we have our current lab set up for automation with our liquid handler, our solid handler, and our hyperspectral camera. On the right here, we have a possible iteration for the next evolution in our lab, where we add a mobile cobot for moving samples from stations to stations. We have characterization, integration of different characterization stations, and then a second liquid handler to increase production even more. So if we go back to our original graph of levels of laboratory automation, after these upgrades and in the near future, we could possibly be looking at a level 3 or level 4 automation lab. Thank you.